So hello and welcome everybody to one of our webinars as part of a man-sponsored series. Today we are looking at a vital topic: carbon capture, reuse and storage. It is especially important since we've all gone through a heat wave and Britain is actually facing the second heat wave in 2 days' time. So it is undeniable that there's a lot, if not too much carbon out there in the atmosphere, and something needs to be done urgently. I'm pleased to be joined by a panel of expert speakers who has the technology to not only capture the carbon, but also to store it either permanently or transport it to another place or even reuse it. First of all, I would like to show my appreciation and extend a warm welcome to Norway, to Janne Harstad Rasten, who has more than 30 years experience in oil and gas offshore and subsea. She is responsible for the carbon team within Aker Solutions renewable segment since November 2020. And she has headed the Amine CO2 catch plant and the research around that at Mongstad, which is rather famous. And she's now also working on Aker's Breivik project. Second is Andreas Nortemann, who joins us from Ludwigshafen, Germany, I suppose. Andreas is very well known in the industry. He has been working on multiple projects with BASF. He is responsible for their gas treatment technology since 2005, and he has been working on projects with RWE, Linde, and with the Porthos projects with most of the some of the big oil majors like Shell and others. So from over in the US, I'm joined by Andrew Baxter, who founded Sustainable Energy Solutions and made it a success to the extent that it actually was acquired by Chart Industries. He's still working in his field and has a wealth of experience on CCS, and they've developed a special kind of technology into which we will go later. Then we are pleased to be joined by somebody from out in the industry, actually. Somebody of the Tenaska is the largest power generator, or one of the largest power generators in the United States. We are joined by Manuel Herreis. He is Business Development Director, Carbon Capture and Storage, and Tenaska has set up a series of CCS hubs, and this is helped by a regulatory development, the so-called 45Q tax credits, into which we will go in a second. Then from back home in Berlin, we are joined by Peter Klotsche, Head of Sales, Carbon Capture and Storage at MAN. Hello. Peter is, he told me earlier, he's the compression guy. So he has a wealth of experience in compressions and in engines. And he is working with several of the ladies and gentlemen on this panel on various projects. So without further ado, Manuel, can you please highlight the role and importance of CCS today?
Of course, thank you, Anya, and thank you to everyone for attending this webinar with wonderful panelists. It is my privilege to do a sort of an introduction, which I think comes of no news to anyone here. But as we all know, IPCC and the Paris Agreement established the goal of limiting global warming by 1.5 degrees Celsius with respect to pre-industrial levels. And as of the latest report, it is estimated that global temperature has already increased between 0.8 and 1.2 degrees Celsius. And at the current pace, it is forecasted that we'll reach 1.5 before 2050. We are constantly reminded of the devastating effects of severe weather events, such as heat waves, that are becoming more and more frequent. And just as an example, a warmer cloud can carry more water vapor than a colder cloud, thus generating heavier rainfalls. And we've seen a bit of that here in the US as well. So what does that have to do with human-made CO2 emissions? Well, for one, CO2 is the main greenhouse gas in our atmosphere. In 1960, there were a total of 15 billion metric tons of CO2 emitted into the atmosphere. Fast forward to 2020, it was 40 billion tons, almost 3 times as much, bringing the estimated cumulative emissions to more than 2 trillion metric tons of CO2, and very dangerously close to the limit of 2.5 trillion tons that will cause 1.5 degrees rise in global temperatures. Effectively, this means that to achieve this goal of limiting global temperature rise to 1.5, we must achieve global net zero by 2050. And that needs to start right now. And it will not be easy. According to the Energy Information Administration, or the EIA, in 2020, fossil fuel electricity generation dominated the industry at 60%, compared to quote unquote low carbon energy at 40%, which includes renewables and nuclear. Therefore, it is unrealistic to think that we will be able to ramp up low carbon energy quickly enough to replace all fossil fuels. This is where carbon capture, utilization and storage, or CCUS, comes in the picture as a tool in the toolbox to allow us to continue using our current energy infrastructure and still reduce or eliminate emissions, and potentially even have a net negative carbon footprint. Today, the world is capturing and storing 40 million metric tons of CO2 per year. The EIA scenario for net zero by 2050 is calculating that we need to improve that into 1.7 billion metric tons of CO2 per year. And this is by 2030. So it's only 8 years ago. That means 4,000% growth.
Wow.
In addition to that, direct air capture would also have to ramp up to 85 million metric tons, whereas today it's effectively negligible. Finally, although CCUS is nothing new, and we'll see that later as we discuss more the projects and the technologies available, it is at least now finally translating into policies that will enable the rapid growth of CCUS, and incentives like 45Q in the US, carbon tax in Europe and Canada, and offset markets are key contributors to both public and private investments.
Thank you, Manuel. Thanks for giving this overview and for showing the urgency. Janne, I understand that the market is undergoing tremendous growth from 2.8 billion last year up to an estimated 500 billion in 2040. Do you see that growth, and what needs to be done to make this happen in an economic way without too much tax credits? So how can we bring the costs down to achieve that growth?
Thank you very much for your question, Anja. I agree, the market is huge. I have seen curves from analysts confirming the figures you mentioned. For instance, Rystad Energy have slightly more positive or higher values than what you said, and we need to, it's a huge capacity, and also compared to what you said, Manuel, this market should be very, very big. Today we have 29 plants in operation, and with the 40 million ton per annum, as referred to you, Manuel, per year is the capture rate. We have another 141 plants under development, but to reduce the climate effects, the world need 100 times that to be net zero in 2050. One big challenge is in this market today is that it's in a large magnitude politically driven, and it is a bit difficult to predict the future or how this take off, because we see that decisions are delayed, and it's a bit difficult to plan. But it's obvious that we need to do something to save our planet. My take is that I think we need to pay taxes for pollution. to have a drive because if today it costs more to capture the CO2 than the taxation. If that had been the different opposite, then there had been a driver to invest in carbon neutral solutions. And we are human beings, and we need some drivers. If it doesn't hurt our own budgets, we tend not to do it. So I think we need some drivers, and we need some brave politicians and decision makers to make this take off.
Yeah, absolutely. I cannot agree more. Andrew, in the US, something is cooking and something is actually materializing. Tell us the latest on the 45Q tax credit and how this helps drive the industry forward.
Yeah, just last week there was kind of a breakthrough. As Jana said, this is a kind of a political issue in terms of the regulations that drive the adoption of this. And so in the previous administration, a tax credit called the 45Q tax credit was put in place that provides a tax credit incentive for capturing and sequestering CO2 in the US. And this is the broadest incentive in the US by the federal government to incentivize CO2 capture and sequestration. And so just recently, an agreement was reached in the Senate on a bill that is actually called the Inflation Reduction Act, but part of that bill includes an extension of the 45Q tax credit. So that, just to be clear, has not been finally passed yet, but an agreement in principle among the majority party has been reached to put forward a bill for vote. That would extend the 45Q tax credit language so that any project that commences construction essentially before the year 2033 would qualify. So right now it's before the year 2026. So you get a 7-year extension on that. There's also some parts of that that would result in a direct pay rather than just a tax credit. Also an increase in the value of the tax credit. I think a really important part of this is also a lower capture threshold. So especially for developing technologies, that lower capture threshold to qualify for the credit can incentivize smaller plants that we need to build in order to go to the larger plants down the road as well. So it's promising from kind of the perspective of what Jana said, that we really need politicians to take action in order to incentivize a lot of the adoption that we need to address the climate change issues that Manuel was referring to.
Thank you. Yeah, sounds like it has helped. It helped to bring some clarity, and hopefully some more investment will come forward also in smaller projects. Peter, let's look at the technology side of things. So from a perspective of a consultant, let's say, what technologies are out there and which ones are applicable in which situation? What is your view on this or your experience in this field?
Thank you, Anja. Well, I'm in a lucky position that since we are doing the compression of the CO2, I can look at all the capture methods which are, let's say, on the market, because we get all those inquiries. And most common and most major, of course, and I think that Jana will elaborate on this, are, of course, the chemical absorption process using amines, for example, alkalines, but also physicals, like, for example, Selexol, Erectisol processes, which are very mature and are being used more than 50 years now. We're seeing, but now, however, coming up other technologies, like, for example, hybrids, which can be a combination of cryogenics with membranes, but also cryogenics, for example, with absorption, with pressure swing absorption. And we see a big future in the membranes, especially in the so-called MOFs, metallic organic frames, which have big advantages over the chemicals because they are not poisoned and they are, let's say, much more cheaper in the regeneration mode. So actually, let's say, I think that still the absorption, the chemical absorption will play the most important role in the next 15 years. Nevertheless, we're really seeing big movements and big, let's say, efforts to get all this capture processes in cheaper methods. We must consider that still the capture process takes almost 60% of the whole cost. If you calculate 1 ton of CO2, that means that the most of the efforts are being put in these capture processes these days.
All right, understood. Now let's look at the various technologies out there. Let's start with the lady in the group. So Janne, can you please explain the amine technology which Aker has developed?
Yeah, and I also like to use this question to give me the opportunity to explain the difference between Aker Solution and Aker Carbon Capture. Because I experience there are some confusions out there, as we both often are referred to as Aker. For instance, I was presented as Aker Carbon Solution once, a mixture of the two names. The situation is that in 2020, Aker Solutions spun out Aker Carbon Capture as a separate company and it's on the stock exchange market. And with the Aker Carbon Capture, the capture technology went out of Aker Solution and into Aker Carbon Capture. So that is a capture company, while Aker Solution, we deliver integrated solution products and services to the global energy industry. So we are also in the oil and gas industry, we are in low carbon solutions, and we have an example where we work together with MAN on that later. And we also have the renewable segment, and I work as a sub-segment in renewables with CCUS. ACC is that has a technology used on the test center Mongstad project and on Brevik project, and also in some other feeds going on now. And that is a state-of-the-art amine process. Aker Solution is technology independent, and we work with different technology licensors, where ACC is one of them. Could be Andreas, so in the future we can also work together. So back to test center Mongstad. The Mongstad plant technology is based on amine absorption technology using an advanced amine solvent. The solvent goes, it's an absorption process. So the gas go in the bottom of the column and the amine solvent on the top of the column. And then the flue gas and the CO2 react with the amine. It's creating heat. And then the CO2 goes into Peter's system later with the compression for compression and liquefaction. And the amine is regenerated with adding heat to the solvent to release the CO2.
So it's a circular process, basically.
Yeah, it's a closed loop process, and the CO2 released goes then to the liquefaction compression. Right. And it's common to have up to, for instance, 96% of the CO2 captured in these type of processes.
Right, understood. Andreas, how does your technology differ from that of
But I can just add on now that per today, as also mentioned by Peter, the amine technology is very well used for large volumes of flue gas. So it's a state of the art.
Right, okay. So Andreas, how does the BASF's technology differ and compare with others?
Well, I would underline that everything that Janne said, I could have said as well. Yeah, so that's the principle of a chemical absorption desorption process, as it has been, as Peter already emphasized and pointed out, has been known in the industry for, and I would go back 100 years, yeah, because absorption has been done. When BASF invented the Haber-Bosch process to make ammonia in 1915, it also used an absorption desorption process. So that principle is well known in the industry, and I think the differences of Aker and BASF, or you could also name MHI and Shell for that matter, they also offer amine technology. The difference, of course, is on the one hand in the amine, but also on the other hand in the, let's say, in the plant setup, which is very much now a function or a result of the client's needs. So you look at the flue gas composition or where it's coming from, whether it's a coal or an industrial CO2 containing off gas, and it's usually the client then who picks the one solution that fits his project best, or that makes then the difference to his
and the
decision.
solvent, can the solvent be further refined, or are there new solvents in development which might be even more efficient than the ones we already have?
Well, it's a good question, very valid question. I think it goes back to what Janne said before. Yeah, the Mongstad is a test center. Yeah, and I think over the years, or over the 10, 15 years they've been in operation, I think they've tested multiple products, and they are not going to stop doing that for as long as there is R&D work carried out that helps inventing new amines or new solvent systems, new blends, etc., etc. And by the way, our test center was with RWE in Niederaußen. Yeah, it was more or less adjacent to a coal-fired power plant. And together with RWE for 10 years, we have tested solvents until we found the best one, with the highest capacity, the lowest regeneration energy, and the lowest, let's say, degradation problem that you face when you have an oxygen-containing flue gas. Amines usually they don't like it. Yeah, let's put it this way. And so we have been testing that for years. Yeah, for nearly 10 years, have been operating that facility. But there is also, as I said, if the market really is developing in the way that we have described before, it takes all of us.
Right. So apart from the solvent-based carbon capture, there is another technology out there, Andrew. Can you please go into this for us?
Yeah, thank you. And I agree with Andres and Jana. We need, really to reach the goals we have as a world, we really need every solution we can get to address the emissions that are out there. The technology that we've developed is pretty different from what has been described so far. So what we have is not a chemical absorption desorption process. It's actually a phase change process we call cryogenic carbon capture. And conceptually, it's very simple to understand. Everybody knows if you get something cold enough, it will freeze. And that's what we do. We cool down the gas that would be coming out of a stack at a power plant or a cement plant or other industrial plant to the point where the CO2 freezes and forms a solid. And the other gases, mostly nitrogen and oxygen that come into the plant with the air, remain gases. So we're kind of creating a dry ice snowstorm, right, in here. So we get these solid CO2 particles that we capture in our process and separate from the light gases. And one of the interesting things about doing it that way is we separate the CO2 in a very pure form, just like a snowflake is kind of a pure form of water. And then we can warm that CO2 particle up under pressure. So it goes directly from a solid to a liquid state, which is the state that you really want your CO2 in for transportation and storage and for many utilization and use cases. And so that's kind of the fundamental difference between our technology and an amine absorption desorption technology. As stated previously, the amine technology really is more mature, been around much longer, and is kind of the state of the art. We consider our technology to be kind of a second generation technology that is being developed in order to address kind of this changing energy, this being developed to address this energy transition that we're facing right now.
So these are two very different technologies. How do the costs compare, or does it depend on the situation? Why would I choose one or the other? Andrew?
Yeah, they are different. As I mentioned, the amine technologies are more mature. And so oftentimes if somebody's looking to implement something right away, That's an advantage in terms of scaling risk and technical risk, right? Where they would go with those amine technologies. Our projections show that the cryogenic capture can be more cost effective in terms of capital cost and lower energy cost as well. In addition to that, we don't use steam in our process or heat to regenerate like an amine system does. So we don't need to maybe burn fossil fuels to generate steam or use electricity to generate steam. All we need is electricity as an input to our process to turn compressors that are generating refrigerant. And so in that regard, it's an easier retrofit onto existing plants as well. So those are some of the advantages of the cryogenic process.
Right, understood. Okay, there's a question out there from the audience. I'd like to address this to Manuel because it fits into what I wanted to ask him anyway. Is there a universally accepted regulatory or legal framework or a template for carbon capture and storage? Because what I was trying to get at is carbon capture in the US now feasible without tax credits, or do we need it? So how much subsidies do we actually need? And if so, what framework would we need all around the globe? Because this is a global market, obviously, carbon capture.
Yeah, I think Janne said it very well before, that we need drivers, we need incentives of some kind, and you can think of it as, you know, the carrot or the stick. So the US has opted for the carrot, meaning we'll hand out money for people who will perform this service. In Europe and Canada, they've chosen the stick model, which is the more you emit, the more I tax you. And both are perhaps equally effective. They're different in the way that they will get implemented, but they both aim to achieve the same purpose, which is the overall reduction of CO2 emissions and the overall capture of CO2. Are they necessary? I think absolutely yes, in one form or another. So you need, like Janne said, we need drivers. So either those drivers come from policy and policymakers, or those drivers come from customer behaviors and customer requirements. For instance, I was talking to a petrochemical customer last week, and they said their customers who buy their plastics and their products are now starting to require them to declare the carbon footprint, which wasn't a requirement. I'm not even going to go 10 years ago. It wasn't a requirement last year. So those kind of behaviors incentivize people doing something about their products, because if they don't react, they will be left out. However, take the opposite effect, and let's say Tenaska as a company chooses to spend a lot of money in doing carbon capture, but it's not recoverable in the market. You don't get a premium in the market. We will essentially go bankrupt and we will lose the business. So this is the balancing act that we need to achieve through policy and driving society behaviors to get there. So absolutely a framework is necessary, whether we let the free market decide what that is, or we do what we're doing now and adopt policies that incentivize those behaviors. I think it will evolve over time, and COVID has helped society change their behaviors. But definitely, there are frameworks, and they are very necessary.
Good. The audience has a couple of questions. So first, there are questions with regards to the cryogenic technology. So what is the energy need for 1 ton of CO2 with this technology today, Andrew? And then he asked for an ideally efficient technology. So in the best possible world, what energy efficiency would you get with your cryogenic technology for capturing 1 ton of CO2?
Okay. Yeah, that's an interesting way to phrase the question. So it's the case that for any carbon capture technology, your energy cost per ton of CO2 is going to be dependent on a few things. a really important one is what the composition of the gas is that's going into your capture system. And so there's a broad spectrum of the composition of gases that you can treat in a post-combustion carbon capture scenario even. So if you're capturing from a natural gas turbine type application, you might have 3% CO2 in the gas. If you go to a cement plant, it can be over 30%. And so to capture the same ton of CO2 in those two different scenarios, you need to process 10 times the gas, right? And so you can imagine that the energy needed will be very different in those different scenarios. But for us, on the low end, if we're on a cement plant, say, and we're at a large scale, so larger scale also helps us get better energy numbers, then we can get below 200 kilowatt hours per ton of CO2 captured. And that's in terms of electricity. So the other thing to keep in mind, as I mentioned before, is we're consuming electricity, whereas these other technologies use heat. And so there's a little bit of a trick to compare heat to electricity, right? And so the comparison, you have to do some conversions to do a comparison there. But that's kind of on the low end of our technology, is below 200 kilowatt hours per ton. On the high end, if we're at very low concentrations of CO2, might be 450 kilowatt hours per ton of CO2 captured from a small gas turbine, for example.
All right, thank you very much for these numbers. Andrew, I have another, Andreas actually, so sorry. Andreas, I have a tricky question which I'd like to address to you. Which type of carbon capture technology least affects the power plant output? So for example, the electricity and heat production. Having worked with RWE, I'm sure you can answer this question. Which type of carbon capture technology least affects power plant output in terms of electricity output and heat output?
Or maybe it's an easy one to answer. I would say the technology that uses the least amount of energy.
So which one is it? Which carbon capture? They want to know which kind of get you out of the reserve to kind of give some numbers around your technology.
Yeah, I would, I don't know, I would go with the Andrew answer. It depends, yeah.
All right.
Depends on the power plant. It depends on what which, I don't know, assuming it's a fossil and not a bio-based product, etc., etc. So there is not that single, killing answer to that question, I'm afraid.
And Andreas, also how clever you are in the heat integration between the CCGT and the compression system and all the systems. So, yeah.
Yeah, maybe I can add to this, because we're using, for example, the heat of the compression to heat up the water and produce steam, for example. Now you can save almost 33% of the energy you would need to produce the steam. And also heat pumps are getting more and more important for the process, because as Janne said, and also Andreas, you need a lot of heat, let's say, to dissolve the CO2.
In this context, Peter, there's a woman asking that there was talk about warming CO2 for transportation. Is this actually economically viable to transport liquid CO2? Peter, can you answer this, or Janne maybe?
Yes, I can say something to that. Well, actually, transportation is done at higher pressures. If you want to inject CO2, you would need at least 80 to 120, maybe even 150 bars, if it depends on the depth of the injection point. And it means you will transport it either in a supercritical status, which is at a pressure higher than 74 bars and temperatures above 40, 50 degrees, or you will go to a more or less dense phase, which is more or less liquid, which is the same pressure level, but it's below 30 degrees. Now, both ways are possible, and basically both ways are the right transportation measures for pipelines, for long distances, and also injecting the CO2 into the earth.
Good, thank you.
And I can just add to what you said, Peter, because it's you need to have control on the phase changes of the CO2 when you are transporting it, because CO2 is very special compared to water, because it's a very small part or at a very small range of pressure and temperature. It's in liquid phase. So it's very important to have control on what you do. And I fully agree what Peter said. It very often is dense phase conditions.
All right, thank you. There are various questions on the shipping side of things. So how can carbon capture and storage be useful for shipping? Is there a design out there for creating specific capacity and specific ships for? I'm sure there is. And if we consider the technology on board ships, which of the two technologies is more efficient for capturing shipping emissions? So now we are capturing transportation emissions, basically. Andreas, you're nodding, please.
Yeah, I'm nodding because it's an interesting or good question, interesting question. We've just we've entered into a little bit of a development with a client, with a shipbuilder, actually to doing a feasibility study, what it means to put a chemical absorption and desorption on board of a ship. And we're trying to answer questions like, well, what does it take in terms of space? What does it mean in terms of weight for the ship, etc., etc. What are requirements in terms of required infrastructure? So you need to discharge then at a port if you capture it, and most likely compress or liquefy in order to save space. We are discussing concepts how to whatever is onshore can be with the weight constraints that you may have on a seagoing vessel. And it's an interesting topic where particularly the shipbuilding industry is interested in. They're looking at it seriously. And it's I would say it's still a way to go. There is no solution yet available. But we've started that as a technology provider. We've started that dialogue. And it will probably go on for another 12 or 18 months to figure out whether the chemical absorption, desorption is indeed an option or not.
Good.
So that's an important aspect. I think also the IMO, the International or the Maritime Organization, they have set the new standards. They've started off years ago with the sulfur emissions in high or in emissions controlled areas, like the North Sea or some parts of the Asian coastal lines. So sulfur emissions have been reduced, but we're looking at, for example, those LNG carriers, which usually run on the product they have in the bulk of their ship. So it's all sorts of aspects. What you also need to bear in mind is what is different offshore to onshore is that the stuff is moving. So you have to take that into consideration as well, building a unit, a so-called floating unit.
I have a lot of questions, and so Janne and Andreas, in a solvent-based methods, are the chemicals that we are using actually eco-friendly? If they have reached their saturation point, then what are the possible ways by which they can decompose? And do they actually decompose in an eco-friendly manner?
Maybe I can start. I know the ACC technology mostly, and it's put a lot of R&D into finding a stable amine that is, because the question is very good, but it's to don't have any toxic components and entering out with the CO2. So it's a lot of effort there to clean the CO2 before it goes out on the top of the column. Paper.
The other aspect to add to what Janne said, most of those degradation products are acids, so they will then react with the amine and can be taken out by different means. Like you can use a exchange resin, or you can purify it afterwards after it's been used. You can purify it by other means as well. There are ways and means of doing that, but as I said, most of the degradation products of any amines that are being used today are like formic acid, acetic acid, and their salts, and they usually stay in that amine.
All right. So one question I'm going to answer. Yes, this is recorded and you can hear it later on. Then, Peter, a compression question. Is there a thumb rule percentage with regards to CAPEX for compression systems and pipeline investment for carbon capture and utilization? So they are writing, assuming only pipelines are used for transport and there is no need for liquefaction. So a project where you can do it all by pipeline. What rule of what CAPEX would you
Well, as said previously, maybe I was not clear enough, but you can go both. You can go in liquid phase, we call it dense phase, or you can go in a so-called supercritical phase, which is more or less something in between liquid and a gas. And both are very suitable because CO2 is very compressible. And you compress CO2, you must imagine if you go from 1 bar atmospheric bar, which correspond to 100% flow. If you go only to 74 bars, you're reducing the flow by more than 99%. So it's very convenient because you need less space if you want to sequestrate it. And regarding now, let's say the pipeline, the cost of the pipeline, the cost of compression, typically the share is that the capture unit will have at least 55%, let's say, of the whole cost. If I say US dollar per tons, then compression and dehydration will have in a range of 16%, and transportation will have another 16 to 20%. So actually, the first these steps, which is capture, compression, dehydration, and transportation, they amount to almost 90% of the cost already. And this is why we always look at these 3 points, looking where we can integrate heat, where we can use heat recovery, where we can use other means to lower these costs. Mm-hmm. Yes, and of course it makes difference how long the pipeline is, because as Jana said, if you have a very long pipeline, you inject the CO2 with high temperature, for example, 90 degrees, it will cool down very, very quickly. Maybe it takes only 300 kilometers or 400 kilometers, it will go below 30 degrees, and then it will liquefy. And this is typically what you want to avoid.
Mm-hmm, mm-hmm. Manuel, this might be a good question for you from the audience. For operating costs with regards to carbon capture utilization, and especially focusing on transport, is there a breakdown on how much electricity, how much labor, how much maintenance costs you have? And is the whole process comparable to LNG transport? It looks as if somebody's trying to develop a project. Is there an example percentage of a breakdown we can follow? They're asking.
Definitely, I think, in the industry, we follow the dollars per ton captured. So it's kind of a mix between capital expenditures and operating expenditures. I completely agree with the figures that Peter shared just a moment ago. We do see the bulk of the cost, both in the CAPEX and the OPEX, relying with the capture unit. Whether you include the compression and dehydration there or not is up to you, but it only makes the number bigger or smaller, but it's still the number one category. Transportation, Peter alluded to it as well. CO2 is a very nice gas to transport so long as you can control the phase in which it's in, meaning natural gas, you have to continue to keep compressing it because its viscosity is not as good for transportation, but with CO2 you can go longer distances without having to recompress it. So the operational cost of transporting CO2 compared to natural gas is lower. I'll draw the same parallel. If your plan is to ship CO2, it's also less energy intensive than liquefying natural gas. There's one key difference, however, in that natural gas or LNG is a usable product that has energy content, and as I'm sure Yannick can attest to, CO2 holds no calorific or no energetic content, and so it has virtually no value. So we have this landfill or waste management model for CO2 in which there's almost nothing left to do with it but to bury it underground. So I didn't answer the question, and I can't. I'm not sure most people can. If anybody else has a contribution they want to make to this question, floor is yours.
Well, I also will not answer the question, Manuel, but I'll just say, because it's very dependent, right, on the specific circumstances and situation. But I will say, and I know there have been some questions along these lines, that while the transportation of CO2 is well understood and it's less expensive than the capture and separation of the CO2, it is really important. And in some cases, in many cases, the CO2 transportation and sequestration infrastructure is the biggest thing that's holding up carbon capture deployments. So, you know, getting pipelines built, getting sequestration sites permitted and built is one of the best things we can do to move carbon capture industry forward generally.
Right, that was a good roundup. And now I would like to look at some big pipeline projects out there, big network projects, not pipeline projects, network projects. Let's look at the Northern Light projects up in Scandinavia, up in Norway. And I understand that Janne is involved in that, and it's an EPC project. Phase 1 is already underway, and phase 2 will replicate phase 1 and make it substantially cheaper. So please explain us more how this all pans out and what size there is and who's integrated into this project.
Yeah, thank you, Anja. I think many people around the globe has heard about Northern Lights project. That is a transportation, storage and injection project under this Longship funding from the Norwegian government. And it's actually, to my knowledge, the first and only sanctioned injection project in the world of this size. And phase 1 is underway, is under construction as we speak. And Aker Solutions was the lucky winner of the EPC contract for the terminal. And I know Peter has something to add after me from his company. And it starts with the 1.5 million ton per year as a capacity. But phase 2 is underway, and that will utilize the size of the pipeline to the maximum extent, and the rate will increase to between 5 and 7, 8 million ton per year through the system. And then is where we come into this, because the phase 1 is first of a kind project, and what the client and the industry want is that for phase 2 it's copy and scale. Mm-hmm. And that the learning from phase 1 can be used into phase 2 to get the cost down, which will be very important, and then also that this can be copied on other sites afterwards. But I also like to use the opportunity to mention Sleipner, and it's back to a lot of the conversations earlier, and maybe mostly back to what you said, Andrew, because in the late 80s, Norwegian government put tax on pollution, CO2 emissions from the oil industry, and that created a lot of new technology to avoid paying that tax. And one big one is on Sleipner, because on Sleipner it's an offshore amine plant for capturing CO2 from well stream, and it's roughly 1 million ton per year in capture in CO2 captured. And that with the tax, it was so expensive not to build a compression and liquefaction system and an injection system that the owners of the field decided to do that. So it has been injected CO2 from the Sleipner field since 1996, 97-ish. So for more than 25 years, 1 million ton per year. And I've heard people say, but does it leak? No, it works, but you need to be in the right geology. You need to have a cap above. And I had to say to this audience that old gas fields, there are a lot of opportunities to dispose CO2 permanently. Mm-hmm. and the North Sea basin for Europe is perfect. It can capture, I have read the number, 60% of Europe's emissions for years. So there is a solution, and Northern Lights is a first of a kind. And I hope there will be many more, because if you don't have injection storage, then what do we do with the captured CO2?
So quick question. The North Sea is perfect. Which other geologies are also perfect? Not that you might be involved, but which other parts of the world would also be perfect for replicating this Northern Lights?
Yeah, you need to have a stone that doesn't has stopped the permeability of the gas, so it block the gas, and then it should be safe from earthquakes, etc.
And can you point at some regions? The US has some.
No. I know that it's studied in Australian waters. So I assume that is a good place, but I haven't been working with that person personally.
Yeah, I can speak on the behalf of the US and Tenasca. We have been doing quite a bit of geological characterization and screening studies across the US. There's better and there's worse, but generally speaking, what Janne is saying is absolutely correct, that you need what we call pore space now, which, to its own name, it's a porous geological formation that allows CO2 to fill the gaps, if you will. And it's topped by a cap rock that we call, which is a sealing layer of rock. So long as you have those two, we'll keep it general. So long as you have those two, you have good potential for sequestration of CO2. Now, in the US, there are a number of areas that have been identified as being very suitable for economical sequestration in high volumes, and so a lot of that is in the Gulf Coast, in the Gulf of Mexico, in the Permian. Echoing Janne's comment, generally where you have had historical oil and gas production, you're bound to find adequate geology for sequestration as well.
So basically, in the Middle East, there should be possibilities as well.
Yeah, following that principle, you are right.
and they are being looked at, yes.
All right. Just asking. Then we have another huge project out there in the port of Rotterdam, and Andreas is involved in that. Please tell us about the Portos project.
Yeah, I'm not, maybe there are too many project names out there with too many parties involved. So BASF, we are not just a technology provider to the capture industry or to the gas treating industry for that matter. But BASF, of course, as a large chemical company, we're also a big emitter of carbon dioxide. Yeah, so BASF and Portos, as you said, is a big project. That looks at capturing carbon dioxide in the port of Rotterdam, and the founding companies of that consortium, which is a topic we will probably come to in a second. It's the Exxon, Shell, Total, Air Liquide, and there are multiple refineries in that port of Rotterdam. And they are looking at building up infrastructure to take the carbon dioxide, and as Janne emphasized a minute ago, it has a nice shore to the North Sea. Yeah, there are quite a few oil fields that have been produced not too far offshore or in the vicinity. Let's put it that way. So that consortium is looking at collecting the carbon dioxide and then pumping it offshore or taking it offshore, liquefying it and taking a ship. That's still probably part of the discussion. And then there is Antwerp at sea, which is a similar project. It's like Antwerp, and with the @ from the email address at sea, and sea as the letter C, but meaning the sea out there. And then there is a third project. It's called Kairos, and Kairos is a BASF project. together with Air Liquide and the Flemish government in Belgium, where Antwerp is located, and it's BASF's second largest site in Europe. And that Kairos project, it goes in a similar direction as Janne pointed out before. So the intent is to take just over 1 million tons a year of carbon dioxide from our Antwerp operations, and then using the Air Liquide's CryoCap technology, which is a bit of a competition to Andrew, I believe, because it's also a cryogenic. It's a liquefaction part, where we have the OAs, where we separate it from some of the plants that are big emitters at our Antwerp site. And then Air Liquide is compressing and liquefying the product. And then the question at the moment, and that's still undecided, is whether we liquefy and ship or whether we pump. And now Porthos comes back in, with that cross-border, bringing it to the Netherlands, because Belgium doesn't have that much oil fields off their shore, but the Netherlands have, or I'm pretty sure they're also in discussions with Norway, whether it's an option to ship to some of those depleted oil fields there. And there are two aspects to it. One is the cross-border aspect in Europe, which is an important thing to look at, and you find more and more consortia developing those projects. And Northern Light is a consortium of corporations and public that have a joint interest. And so is Porthos, as well as Antwerp at Sea. Both are flagship projects as part of the European Innovation Fund. And so there's plenty of activity, and I think it's also those easy it's the easy CO2 with partially available infrastructure already, and that's what may make them really successful.
So it's impressive, and it's 3 huge projects, but looking into the future, Andreas, now we have Europe, we have European funding, we have nice European helpful regulations, but the oil majors, they're also involved in Asia and especially in the Middle East. So would they now look at the Porthos project or look at the Port of Antwerp project and say, we want to have the same thing in Saudi Arabia in 5 years' time, or in Malaysia, or you name it? What do you think?
Well, I think if you look at the, let's say, take the Qataris, they have plenty of LNG capacity. They're building more. They also have a carbon capture and storage regime ongoing. Take a look at Saudi Arabia. They're building blue hydrogen plants to feed their processes. So I think it's spreading. It's like, and as we said before, I also agree with Andrew and Janne. It takes the courage to sequester. It takes the courage to build up infrastructure. And that cannot only be done by corporate. That needs policy, and that needs an incentive or a penalty, and it has to be borne by society. Otherwise, it's not going to work.
And the Middle East, do they have incentives, or is it purely market-driven out there?
No, I think there is also it's market-driven. There is a realization that the world and society means to really move away from, or at some point in time, to move away from just burning fossil fuels.
Maybe I can amend a little bit and just to say that the Middle East is very focused on enhanced oil recovery, which was the focus also in the US for the past years. We're seeing now more and more coming to sequestration only for capture because of the 45Q tax. Nevertheless, Middle East is strongly driven by this enhanced oil recovery because they still have so much oil, and they will use it for the next, 30, 40 years. So they have both. They can capture CO2, but they can use it as a utilization.
Right. What I'm trying to get at, is there a region where there is no nice or supportive tax regime? Maybe Andrew, you can answer this question. So we have supportive tax regimes in Europe and in the US, that's clear. But we have also big oil production or oil and gas production regions, the Middle East, Australia, Malaysia, and small like Nigeria. Is there a way, or are there places where carbon capture and storage is viable without support?
So yeah, that's an interesting question. At a very large scale, really regulatory support, I think, is needed for carbon capture. At a small scale and niche markets, we have looked at opportunities where CO2 can be produced not as a waste stream, which is kind of, as Manuel described, that's the large scale model that I think we really have to follow. But we have looked at opportunities to produce CO2 as a product that can go into existing or new supply chains. And so we're looking at projects. One of the advantages of our technology is we can relatively easily produce CO2 at a very high purity, even reaching food and beverage grade levels of CO2. And so we've looked at projects where you can produce 100, 200, 500 tons per day of CO2 and have that go into some kind of value add process, or just sell it into an existing supply chain. So I think there are niche markets where that makes sense. But when we're talking about doing something about climate change, you really go to this model where you have to store the CO2 underground, as everyone has been describing here,
Right.
and infrastructure like pipelines to do that.
So this adds right nicely into the next question I wanted to ask you. You have a project where you retrofitted a cement plant in Alabama with CCS, together with Carbon Cure, and then you sold off that carbon. So I'd like to know at what price, probably you're not going to tell me, but how much did this monetizing a waste product help to get the project economic? And then there are more cement plants out there in India, China, you name it. So is this a model which you've developed out there in Alabama?
Yeah, the cement industry is a really important industry for carbon capture because it's part of what is referred to as hard to abate industries. You can't produce cement with a with a solar panel. You can't avoid emissions by just using renewables there, because the CO2 is a natural byproduct of the chemistry of making cement. And so cement is a target, an important target market for us. We have a partnership with FL Smith, a big cement engineering company. And as you said, we've done projects in the past, one of them with Carbon Cure. So Carbon Cure won the Carbon X Prize a few years ago here in North America. For the first 2 phases of that Carbon X Prize, we were the capture partner for Carbon Cure. And as part of that, we went to the Argos cement plant. As you mentioned, in Alabama, we captured CO2 from the cement plant there and produced it as a liquid in tanks, and then gave that to Carbon Cure, and they used it to cure concrete made from cement from that same plant. So that was, as far as we know, the first time that full life cycle of capture and use within the cement space was done. And we have a project going on in Missouri to build a pilot scale capture system at a Eagle Materials plant near Independence, Missouri. And so we were very active in the cement space, and it is a really important, carbon capture is a really key technology for cement to decarbonize. Right,
but to what percentage of your operating costs can you get in by selling the carbon, roughly?
So when we talk about CO2, without regulation supporting it, the CO2 market globally is very regional. CO2 prices vary a lot from location to location. And so part of what I mentioned in terms of niche markets where carbon capture could make sense without regulation is finding the markets where you're not necessarily right next to a geologic source of CO2 or a high concentration source of CO2 that's already there, but finding markets where either the anthropogenic CO2 you can capture is valued by the customer, or you just don't have a good source of CO2 that competes. So just as an example, you can go from $15 to $400 per ton of CO2, right? Even within the United States, depending on where you are, because transportation costs are relatively high for CO2. And so geography matters a lot for the CO2 price.
All right. Okay. So there's no easy answer to that question. I understand. Fine. Then one of our most active person to ask questions out in the audience is asking the same question which I have on my list. He or she is writing, the CO2 can be used to produce a synthetic methane, for example. So Andreas, this is for you. How can this be used? At what cost? And yeah, can we use it to clean up petrochemical industries, or can we even burn it as a transportation fuel? What is doable by synthesizing the CO2 into methane?
Yeah, I mean, in order to make it really viable, green hydrogen is needed. Yeah? So if you take carbon dioxide and convert it into a different chemical, then usually you would start off with hydrogen, and then you get either methanol, or you get formic acid, you get formaldehyde, you get methanol, and ultimately you can also get methane. Yeah, you can convert it back into methane. Now, methane today is used to make hydrogen and carbon dioxide. That's then used to make urea. So you can, technically speaking, you can go full circle. And that chemistry has been looked at multiple times. There is still R&D work ongoing to improve that process. Now, usually carbon dioxide is a dead animal, or has a very high barrier of being converted into a burnable fuel, but it is possible. You would want, as I said, you would need green hydrogen. But if we talk about, if I take what Andrew just said, so you take $400 a ton for the carbon dioxide, and then you have green hydrogen that's produced by electricity from water. Then you add another significant cost element, and that competes, of course, as of today, with potentially methanol that comes from fossil fuels with carbon sequestration. Yeah, so it's doable, and it's a cost element. And the question comes to society then, or looking at Manuel and Janne. Is the carrot big enough, or is this stick hard enough and whether that's bearable for us or not? And in my opinion, I mean, carbon capture or converting all the carbon dioxide back into a chemical, from a chemical perspective, may not make an awful lot of sense. If you look at global methanol market, I don't know, maybe 200 million tons a year. Now, earlier we talked about 1.5 or 2 billion tons of carbon dioxide. Yeah, so that exceeds the chemical market by far. So yes, it's an option. It may be an option for somebody in a remote place where you need either whatever chemical, but I don't think it would save the world. Yeah, so doing something or doing little is good, or converting maybe CO2 back into something meaningful, whether it's biomatter. So like the greenhouses that are being, or where you use some of the carbon dioxide in the Netherlands is an option. Converting it into some chemicals is also wherever it's possible and feasible, where it makes sense. But I don't think it's going to happen on a large scale. You rather take the hydrogen and burn it by itself, as opposed to converting CO2 back into something meaningful.
But we still have somebody, so even if the petrochemical industry doesn't need so much CO2 compared to what is out there, that's clear. But we have the transport sector. So somebody is asking, might there be feasible use in the transport sector? And if so, could we then even take CO2 stored underground back up again for creating synthetic fuels for fueling our cars?
Okay,
Janne, Andreas,
or maybe in the transportation industry, take for example the airline industry. I mean, that's a very difficult one. My passenger car, I could technically speaking, I could buy myself an electrical vehicle, make sure that I have a PV cells on my roof, and then hope for sunshine, and then I can drive a car. And 10 years down the road, I'm pretty sure there will be multiple cars available that have all the sufficient gizmos that I would want as a car driver. Yeah, so that's that may be well, maybe sort of an easy one. Yeah. Talking about the aviation industry or the airline industry, and then taking us from A to B, or getting a battery into an aircraft, you won't take off anymore.
But
so
the
you need
fuel.
no, what I'm saying is what you need is liquid fuels. How much you need and how they're being produced, that's a totally different matter.
Right.
Or how much are you willing to pay
Exactly.
for a flight from Frankfurt to Singapore, or from San Francisco to New York?
Janne, do you want to add to this, please?
No, I just want to say that in Norway we have, I think it's most of the cars sold this year is electrical cars, of the new cars. I'm driving an electrical German car myself. But what was really interesting and first time for me to experience this year was to go with a quite big ferry. Well, that was also electrical. That's the first time I have experienced, and it's coming very quickly. But that's electrical. But I think what is important is where you don't have electricity, then of course hydrogen could be an option for zero emission fuel, for instance. But it costs more to produce hydrogen than to produce some other type of fuels.
So
maybe something that kind of partially addresses this question, just real quick, Anya, is Andreas mentioned earlier that if you're going to produce fuels, that you need to think about the secondary emissions, right, that go into those fuels, which is why he was saying you need green hydrogen to produce green fuels. You could imagine a scenario where you use geothermal heat to do some kind of conversion in a similar way, right, to try to use a renewable energy source to convert CO2 into something more usable. But as everyone else has pointed out, in terms of just the energy cycle there, right, if you start with a hydrocarbon and then you take the energy out and it turns into CO2 and then you go back into a hydrocarbon, that's an energy losing cycle, right? You don't gain by doing that. So you need to have an input that is, you need to put energy into that system, and the energy you put into that system needs to be low carbon, or else you're actually creating more emissions.
Right, thank you very much. There are a lot of more technology questions out there. So I read one out, and whoever wants to take it, please go ahead. Many amine or other CO2 capturing chemicals are equally likely to capture SOx molecules as they do capture CO2, meaning an emitter with SOx in the feed gas will have to implement an expensive SOx scrubber before they go for their amine-based carbon capture system. Are there any systems that are not sensitive to SOx that are commercially available? Who wants to take this?
Well, let me maybe first say that I hope that nobody is emitting SOx, because they cause acid rain, and they should have taken measures already to take that out.
Right.
So we do run into a lot of applications, right, where there's different levels of SOx emissions, whether it's from burning coal or biomass, or also cement can have SOx emissions coming out there. And so I do know that some amines are very sensitive to SOx emissions, and there are efforts to try to come up with amines that are less sensitive.
Usually, maybe to add to what Andrew said, usually, well, if there is SOx, and even if it's a ppm level, you would have a pre-treatment, because the SOx also reacts with the amine more or less irreversibly. It forms an acid together with water, and that blocks the amine, and that reduces the capture capacity of the amine for the carbon dioxide. So you want to take it out. And usually, in Germany, in the 80s, all power plants, we were burning a lot of brown coal containing some sulfur, not an awful lot, but some sulfur. All of those power plants were equipped with a flue gas desulfurization unit, yeah. And that's something that, you know, maybe everybody should have from a different perspective.
So in cases where there are not those emission controls in place right now, one thing that we talk about with the cryogenic capture technology is the ability to capture SOx and NOx and mercury in that system. In addition to that, so you know, the cryogenic technology does handle some of those pollutants more robustly than other technologies. Some major learnings from early demonstrations funded by the DOE in the United States were that SOx was a problem for some of the amine technologies tested.
Going back to the geology, they're very interested in the project in the US and in Europe, and also about our mention of Australia. But people want to know if there are other suitable technologies out in Asia Pacific. Who wants to take this, Janne or Peter?
Well, maybe I can pick up a little this one. Let's put it this way. I think the music is playing in America and it's playing in Europe. I would say at least 60 to 70%, maybe even more, of all the projects are within these regions. Nevertheless, we've seen Middle East coming up now, especially in this enhanced oil recovery business, but also, let's say, coming up Southeast Asia, and of course the big still sleeping giant, which is China.
Yeah,
China is in a mode of wakening up and kind of catch up mode, because they have realized as the biggest emitter, almost 30% is out of China, that they have to do something. Nevertheless, they have the plan to go to net zero is longer than in Europe and in America. It's more or less 2060 only, not 2026. So more or less the peak of CO2 will be reached in 2030 only. So it means they're starting now. They have a lot of pilot plans, especially Sinopec and CNPC are working on that. But we expect the big growth in Asia, especially, let's say, propelled, let's say, by China in 5 years only. And then it will catch up very rapidly. I think maybe from here or in 7-10 years, China will have 30% of the capture business then.
And what sectors do you see growing the fastest in China? The post-combustion power generation?
Yes, it's post-combustion, especially power generation, because China needs a lot of power. Nevertheless, there are also other industries like the cement industry also, but also chemical industry.
Okay, right. Some people are asking about what sorbents you're using. Guess we're not going to answer these ones. Then let's wrap up and ask Janne. We have a lot of technology out there. We have various projects. We are proving the point that things are feasible. Where do we go from here, and how can we increase the speed and the urgency of implementing things and getting things done to reduce carbon emissions?
The short answer, Anja, is to go from talking to acting. But I think it's quite dramatic what we have seen over the last year with the increase in CO2 concentration in the atmosphere. It's measured, and it's increased by 40% from 1960 to 22. So few years, high increase. So it's obvious that they need to do something. What is less spoken around is the effect of the higher CO2 concentration and what that has on the sea and the water and the seawater. There are universities, institutes following that as well. And the surface oceans have recorded about 0.1 reduction in pH since we started the Industrial Revolution. That is scaring, because that is a blink of the eye in a geologic evolution time frame. And the seawater has per now absorbed 30% of the emissions. So that is good for the atmosphere, but bad for the sea and the life in the sea. So is there a hope for the future? And I would say yes. We have solved problems before. It's been mentioned here, the SOx, and we had the soar rain in the 70s when I was young, dead salmon in rivers, etc. That is solved. We had the freon gases destroying the ozone layer in the atmosphere. That is improved a lot. And there are others. It's a lot of those examples. I think this animal we are talking about here is much bigger and it's super global. So, but what is good is that we have the technology, we can do it, and we have different technologies, and I think we need them all. And we need the development of new technologies because we need to get the cost level down to get all this project running. And we need all the companies, as mentioned before in this debate, all hands we can have to solve this global challenge we have. So it's, and I also think it's important for us to look into, because it's not net zero, or it's not 100, 1 or 0. It's, I think all we can do helps the global environment and our climate. So I think it's important that we don't see this as a too big problem, but even I can do something, all of us can do something in this. And then it's the push to the decision makers. I think we need the drivers, which we have discussed a lot during this 1.5 hours, because, and we need to act quickly because we pollute so much. We polluted last year 36.3 gigaton of CO2 into the atmosphere. It's enormous figures. In 1900, it was 1.9. So it's enormous, but we had to do it together. And I think I think it has to cost to pollute. Mm-hmm. I'm talking about myself. If I had to pay, I spend less. And that I think goes with all of us. So we need to get the cost down. We need all the type of technologies and good work going on. We need to get more and more efficient technologies that I'm sure will come in the future. Very interesting to listen to the cryogenic process. So I end with saying, so let us go from pollution to solution.
Absolutely. So thanks to everybody for talking for 1.5 hours, and now we try to speed the project up, and also I will feel free to hand out your email addresses. Some people have asked for you guys or girls' email addresses. Hey, this is a compliment actually. So people are very interested. There are people out there in India who've been quite pushing to get your email addresses. And I thank you a lot for this lively debate, for all the information and all the numbers you've come across with. And so hope to see you soon in the near future. We have a Power to X webinar coming up on the 11th of October. So maybe you want to listen in, or let's see. Have a good summer, enjoy your holidays, and thanks again. Bye-bye.
Thank you very
much. Bye-bye, and thank you, Anja, and to the organizers, and all good.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Thank you.
Bye-bye, and thank you for listening.